Hello, everyone. Welcome to the Casual Causal Podcast, episode 9. Today, we have one of the greatest causal experts out there, Dr. Nick Huntington-Klein. He's a very versatile person. He's the author of the famous book, The Effect, and also a famous YouTuber. Dr. Nick, welcome to the show. How are you today?
I'm doing well, thank you.
Great. Nick, you're the author of the book titled The Effect. I really like the title. What was the thought process in naming the book?
Yeah, well, the thought process came down to, when you're working especially in applied social sciences, right? So many of the research papers that you see talk about the effect of something, right? The effect of, this policy on education or the effect of education on income. And so it seems like what people are most interested in doing when it comes to applying causal tools is finding the effects of things. So I figured that that would be a good way to sort of signal what kind of work we are focusing on.
Mhm. Um, what is causality according to you? Can you explain this in three levels of difficulty? I'm taking the inspiration from the Wired, where they had five levels of this difficulty, but here we're just going
Sure.
to, have just three levels of difficulty, starting with grandma, a college fresher, and then a causal expert.
Yeah. So I'd say starting at the most basic level, right? So causality is when you want to know how one thing affects another. Right? When
Mhm.
you turn on a light switch, it makes the light come on. So you turning on the light switch has caused the light to come on. That's sort of the basic level. And that when you're doing research, what you are trying to do is you're trying to figure out in the world how one thing causes another. When you take a pill, it might cure your disease. How do you figure out whether that has actually happened or not, right? Or do you just get lucky and you happen to get cured at the same time? Going up a level, I'd say, we're looking at the causes of things, right? We want to know how one thing affects another. However, there's a lot of difficulties in trying to do that. Right? Ideally, we would just be able to say, okay, well, we took some people who took a pill. We want to know if the pill cures their disease. So we should just be able to say, okay, well, the people who took the pill, they got better. The people who didn't take the pill, they didn't.
Mhm.
There's something that's called confounding factors, which are things that sort of show up and get the credit for work that they didn't do, or get the credit for work they didn't do, or make something else get credit for work that they didn't do. So let's say that we're talking about this pill that you want hopefully makes you better, but also, the only people who are willing to take the pill were already pretty healthy in the first place for some reason, right? Maybe the pill does not taste particular. Maybe the pill tastes really good, and so people who are already really sick are good. They just don't feel like eating. They don't want to take a pill. But if you're already feeling okay, you're like, this pill's like candy. I'll take it. Well, in that case, what you're going to find is people who take the pill are healthy because they were already healthy in the first place, right? And so causality research is all about trying to tell, well, what's actually responsible for you being healthy? Is it because you took the pill, or is it because of some other confounding factor? How can we separate these two things out?
Mhm.
Um, Going up another level, so we want to be able to distinguish these different causal effects from one another, right? How does one thing cause another? Um, and how do you actually do that, right? What are the processes that you can take in order to separate those things out? And the classic thing that you can do is run an experiment, right? You want to know whether a pill makes somebody better? Well, you take a bunch of people who are sick, you randomly give half of them the pill, you randomly don't give the other half of them the pill, and then you see which of them get better. The fact that you randomly chose who got the pill or not allows you to ignore a lot of those confounding factors. Like, yes, somebody was already healthier than somebody else. Yes, somebody was wealthier than somebody else. Yes, there's a lot of differences that we can't account for, but when you randomize, it all sort of washes out. Okay. But what can you do, if you can't randomize, right? If there's a case, there's a lot of cases where you would not be able to randomize, it wouldn't be feasible to do, or it would be unethical to randomize. Like, let's say we want to know whether, smoking causes cancer. It would be unethical because we're pretty sure that it does. It'd be unethical to say, okay, well, we're going to randomly say that you 50 people, you go start smoking, and we'll just check in on you later and see if you got cancer, right? You couldn't do that. Um, and so you have to think about the ways in which you can separate out the different causes without being able to run an experiment. right? And in a lot of cases, that comes down to finding real world situations that mimic an experiment. Like maybe, for example, some people live in an area where it randomly happened that, a bunch of cigarette tankers were lost, and now cigarettes are way more expensive in those areas. So people are going to, basically at random have to pay more for cigarettes and therefore are less likely to smoke, right? That could be a sort of something that looks like an experiment that sort of randomly assigns people to to smoke cigarettes or take a pill or whatever it is or not, and others to not do it. Right? In that case, you can compare them. Or if you understand very well why it is that some people get treated and some people don't, you can use statistical procedures to adjust for those confounding factors, leaving yourself just with the cause that you're interested in. You say, well, some people smoke and some people don't because they're more risk taker, because they care more about their health or not, because of all the different reasons why somebody might smoke or not. If you can actually get at all of those reasons and understand what they are because you understand the process so well, you can actually use statistics to get rid of them, to say, hey, I'm not going to allow for the fact that some people are more risk taking because I'm going to statistically adjust for that if I have data on it, leaving me just with the effect of smoking on whatever health outcome I'm interested in, or the effect of the pill, or the effect of the policy, whatever it is.
Mhm. That was an excellent explanation, Dr. Nick. Coming back to the title of your book, right? The effect. Are all effects causal?
So are all effects causal? So I mean, it depends what you mean by effect. I think a lot of time when people use the word, the effect of one thing on another, they're implying a causality, whether or not they technically mean it, right? When we talk about the relationship between two variables, there are different ways that we can describe that relationship that, are saying causality or not, right? So when you say, cigarettes have an effect on health, you are implying a causality there. Whereas, if you say, okay, going to the opera has an effect on your health, right? Again, you're sort of implying that one of those things causes the other, even if what you really mean to say is that those two things are correlated with each other. So I would say that yes, all effects are causal
Mhm.
in nature. If one thing is affecting another, then that is a causal effect. But also people call a lot of things effects even when they're not causal.
Understood. Uh, if you look at the field of causality, it is historically been dominated by, two streams, the biostatistics and the economics. Are there any pedagogical overlaps between the two?
Yeah, so there's two big streams of thought in causal inference. One sort of descends from, or one of them is more popular in econometrics and the social sciences, and the other is coming a lot from the biosciences. And really, there's also sort of a third, which is that they don't
Mhm.
have to think about causality very much because they just get to run experiments,
Mhm.
right? And that's the medical sciences, and that is another way of thinking about causality. It's just they can just sort of stop at the experiment stage of things because that's the nice and easy thing, and they can do that.
Mhm.
But in terms of like epidemiology and economics, there is a lot of overlap in the way that they think about it. I mean, really, because they're solving the same problem. So you'd expect that they would come to a lot of similar solutions and think about it in the same way. The sort of philosophical or statistical underpinnings of what they're doing in economics comes from a guy named Donald Rubin, who thought a lot about causality and what's called the fundamental problem of causal inference, thinking about, well, causal inference as a missing data problem, right? If I want to know whether this pill makes you better, I can observe that you took the pill and you got better. And I can observe that maybe somebody else didn't take the pill and didn't get better. But the problem is that comparing those two people doesn't actually solve my problem, because what I really want is I want to compare you taking the pill against you not taking the pill, and I can't do that because that world doesn't exist. There's sort of a
Mhm.
counterfactual world that doesn't exist that I want to be able to compare it to. And so my goal is to sort of try to construct a fake you that doesn't exist, where in a world where you didn't take the pill, right? And that's sort of the philosophical underpinning of what economists are doing. In epidemiology, and these days a lot in data science as well, they're borrowing a lot more from a guy named Judea Pearl,
Mhm.
who uses a more structural approach to causality. The idea being that you are mapping out all of the relationships between all of the variables first, So
Mhm.
instead of saying, I want to observe what you're like if you don't take the pill, you first say, I want to know what are all the things that go into causing you to take a pill, right? Whether I can measure them or not, I just want to know what they are. And then once I have that system, I will then know how to statistically adjust. So to construct that fake you, basically, in the language of Donald Rubin, although they would say more in this, and they would use different language to explain that. Now, mathematically, these are the exact same system, right? You can actually take any mathematical statement in one of those systems and convert it into a statement in the other that is also true or false in the same way. So they're different ways of studying the same thing. So there's actually a lot of overlap.
Mhm.
There are also differences in terms of the kinds of methods that those two things encourage you to focus on, and the kinds of
Mhm.
methods that those things don't. So, for example, quasi experiments are more common in the economic side of things. We focus on them. But what I mean by quasi experiments is cases where you look out in the real world and you try to find, places where the real world has set up an experiment for you.
Mhm.
Because economists tend to be a bit skeptical about the idea that you really can map out the entire system for why things happen,
Mhm.
right? Um, you know, whereas in the epidemiology side, they're a bit more willing to try to map the whole thing out, and so as to adjust for everything, um, which is more in the Judea-Pearl lineage of things. So a lot of overlap, I would say. The
Mhm.
differences are more minor and on the applied side in terms of what things are made easy, what things are made difficult by the two approaches.
Mhm. I come from the marketing science domain, and I think marketeers and economists have a lot in common in the sense that we cannot control for a lot of things out there, and hence we will have to resort to quasi-causal experiments. We will talk about quasi-causal experiments more down the segment. Uh, in your book, you have two separate sections, right? The research design and the toolbox. I quite like the demarcation that you make. Do you think the research design is kind of like a guardrail that kind of prevents somebody from going astray?
Sure. Yeah, so to be clear, so what these two sections are,
Mhm.
so the research design section that comes first is about the question of what is it that you need to do to what's called identify your effect. And what identify means is you are pinning down just the causal effect that you're interested in, right? So I mentioned, I want to know, does taking this pill make you healthier, right? Now, what you actually see in the data, right? You can't observe in the data, oh, this person got healthier because they took a pill. Because isn't in the data,
Mhm.
right? But what I can see is that here's a bunch of people who took a pill and got healthy. Here's a bunch of people who took a pill and still didn't get healthy. Here's a bunch of people who didn't take a pill and didn't and got healthy. Here's a bunch of people who didn't take a pill and didn't get healthy. That's what I can actually see, right? And I can ask myself, well, if I see like a correlation, if I see people who took the pill were more likely to get healthy, right? Why might that have been? What are all the lists of possible reasons that could have occurred? It could be because of the pill. It could be because people who were more healthy in the first place were more likely to take the pill. It could be because people who are wealthier have better access to medical care and they're more likely to take the pill and also be more healthy for other reasons, right? It could be because people who got the pill live in an area where there was not also a toxic spill at the same time, right? Lots of different reasons you can come up with.
Mhm.
And then, just like in a police lineup, right, you're trying to sort of knock them down one by one and leave yourself just with the one that you're interested in. That's identification, right? So, oh, I controlled for wealth. So that's not an explanation anymore. I controlled for how healthy they were at the start. That's not an explanation anymore, right? And you get rid of in different ways all these different explanations until you're just left with one, right? And once you've done that, once you've said, I know that the relationship I'm seeing in the data is now pointing to the explanation I'm interested in, that's when you've identified the effect, right? So the first part of the book, the research design part of the book, is all about how can you ask yourself the question of, well, what do I actually need to get rid of, right? What are those alternate explanations? And what kind of data and adjustment would I need to be able to say, well, that's not the explanation anymore. That's not the explanation anymore. And get yourself just down to one, right? And this is all conceptual. There's no actual math here, right? Because there doesn't need to be, right? Because it's a conceptual question of what are your alternate explanations and what can you do in order to get rid of them. And that's a much more approachable question, right? That is something that you can do even if you're not actually doing research. If you're reading somebody else's research or reading a newspaper study about somebody's research, And thinking about that alone as its own topic allows you to not have to worry about all of the technical details, right? Of all the math and all the programming and all that stuff, which can actually get in the way, right? There's sort of a common problem in applied statistics where we have all these tools, right? We have tools like regression or difference in differences, and I'm going to name a bunch of other ones, right? That we are very used to using. And it's very tempting to say, well, I have this tool, therefore this tool solves the problem that I'm looking at, right? Which it doesn't always, right? Often there's a lot of assumptions that have to go into each tool, and the ways in which a tool could identify the answer to a question, right, relies on a bunch of things being true. But when we have the tool, we sort of forget that we have to assume all of those things, and we just say, oh, I have the tool, therefore I've solved the problem, when maybe actually the tool leaves a couple of explanations unanswered, right? And so thinking about the research design first, that's the goal there, is to think about what is it you actually need to do in order to identify your effect. And then the toolbox is, well, here's a bunch of tools that we often use that if you know you need to get rid of these explanations, here's something that can maybe do it for you, and here's how you would do it for those 9 explanations that you need to get rid of. And so that's why I make that distinction, and why I think it's helpful to think first about the research design. What is it that you actually need to do before you start bringing in what are the specific tools? Partially because those tools can sort of blind us to the fact that they're not magic, right? It feels like here's a button I can push that solves the statistical problem for me. Therefore, the problem is solved. It doesn't really work like that in statistics.
I quite like the explanation that you made right now, that causality is kind of like, ruling things out. Can we summarize it like that? Causality is about, ruling things out, just like a detective work.
Absolutely. Yeah. So causality is all about ruling out alternate explanations. We see in the data a correlation. That's very easy to do. We can always do that, right? But then the question is, why does that correlation exist? And there's always a long list of explanations you can give for any complex system, and then ruling those out one by one is a good way of thinking about it. And often what you're actually doing when you are doing something like controlling for a variable, right? People might have heard of the term controlling for a variable.
Yeah.
That's what you're doing. That's why you would doing it, right? Yeah, you might say, hey, I looked at the relationship between, income and education, controlling for your parents' intelligence level, right? And what that means is, well, if we see that education and income are related to each other, why is that? Well, maybe the education made you earn more money. Maybe it's just because you happen to have better connected parents that got you both of those things. Well, oh, I controlled for that, so you don't need to worry about that alternate explanation anymore. We've ruled it out, right? There's actually a really good analogy that I like, which is with magic, like watching a magic show, right? So I mentioned that system of sort of getting rid of alternate explanations. That's called closing back doors. Right? We have what's called backdoors in causality, where why are you seeing a correlation between education and income? Well, maybe it's because your parents are really well connected, right? And that got you both of those things, right? That's what's called a backdoor, right? I want to go through the front door. I wanted to say, hey, your education caused your income, but there's a backdoor. There's another way I can get out of the house into the same place, which is to say, well, your parents were just better connected. That's a backdoor, right? And when I control for that, I am closing the back door so that the only way you can get out of the house is going through the front door, the one we're interested in. Magic has the exact same phrase. When you're watching a magic trick and they say, oh, here's my hat, I pulled a rabbit out of the hat. And you immediately think, well, I know how they did that, right? There was a rabbit hiding in the hat or their sleeve. You have all the different reasons why that could have occurred in your head. And so then they say, rabbits out of the hat. But look, before they do that, they show you their sleeve. There's nothing in my sleeve. There's nothing in my hat. There's nothing in my shirt. They are closing doors. They're closing down alternate explanations for how that could have possibly happened. And every time they show you, it's not in my shirt, right? That is getting rid of a possible explanation, leaving you just with the goal for the audience in magic is to say, this will leave you only with the explanation of, I don't know how they did that, or that was actually magic, right? They're trying to narrow down the possible explanations to just the one, and they call that process closing doors in the exact same way that people who are doing causal inference call the process of shutting down backdoor paths, alternate explanations for your data, closing backdoors.
So that was a brilliant explanation. I'm never going to forget what is a backdoor criterion ever. Yeah. In your book, you also emphasize on knowing about DGP, that is data generating process. Why is it so important when it comes to causality?
Yeah. So I mentioned the two sort of schools of causal thought, right? And so when we care about the DGP, the data generating process, and what that is that's the real set of laws or tendencies or whatever that explain how the data got to be what it is, right? That's what we're looking at. And so, for example, if I am holding an object and I drop the object and it falls to the ground, why did it do that, right? What's the real set of laws that made that happen? And that's gravity, right? Gravity explains why whatever it is drops out of my hand and falls to the ground, right? And that's truly happening, whether we know about it or not, right? Before we discovered the idea, the theory of gravity hundreds of years ago, gravity was still working thousands and thousands of years ago, right? It was still the actual reason why things fall to the ground when you drop them. Okay, so that's the set of laws that explain the data, right? Why is something in my hand up here, and then when I let go, it's down on the floor? Well, that's the data that I actually have. I can see the learning process is the reason why we see that data, right? So gravity being an example of that. And so if you want to infer causality, right? If you want to explain how different things or how one thing affects another, well, you need that identification process that I mentioned, right? I can see that I dropped the object. Well, now I got to come up with all the reasons. And if I want to say, oh, I got this idea, it's the thing called gravity, right? Big objects attract each other. We got the Earth down there. That's pulling the object out of my hand and down towards the ground, right? And that's what it is. That's why. But imagine that you don't know that it's gravity, right? You've never heard of gravity before. It's hundreds of years ago, right? This is a new idea to you, and you're skeptical. You're thinking, well, okay, yeah, maybe it's this new gravity thing you're talking about. But maybe, like, there's a gust of wind blowing from the top of the screen that I can't see. Like there's a fan up there and it's pushing the pen down, and that's why it fell. Or maybe there's like a witch that is casting a magic spell on the wand that has cursed all pens to fall out of hands onto the floor for the rest of time, right? Or maybe pens are alive and they just love floors, and so that's why it dropped out of my hand when I forgot. Right? All these alternate explanations. Okay, and so if my goal is to say, well, no, it's not any of those things, it's actually this other explanation that I have, I need to be able to rule those things out in some way, right? I need to know, okay, well, yeah, wind does push things. So I need to be able to like tilt my camera up and show you there's not a fan there, right? And so knowing the list of alternate explanations I need to get rid of, right? The things I need to account for, that requires us to know the data generating process. We have to have some idea of why we might see the data that we see in order to be able to explain it away, right? So, let's take the example of cigarettes and health, right? Say, do cigarettes cause cancer? Okay. So, decades ago, they'd not really proven this with enough quality to be able to like pass laws and stuff, right? And so when scientists were first trying to really prove that cigarettes cause cancer, they looked at the data. They said, well, okay, we can't run an experiment. We can't randomly assign people to smoke or not. That would be unethical. We're pretty sure that it causes cancer, but we can't really pin it down, right? And so we can't run an experiment. We need to be able to just use data that we can observe. And they did observe in the data that, yes, people who smoke are way more likely to get lung cancer than people who don't. Right? That's the observation that we have. And so they submit the results, and then the cigarette companies say, well, I mean, hold on a minute. People who smoke are different than people who don't smoke. Here are all the reasons why we might observe that pattern in the data. Maybe people who smoke have different levels of income, different levels of education, different levels of being willing to listen to health professionals, being willing to go to your doctor and get a checkup, being willing to exercise. All these things might be different. And that's true. That is accurate, right? It is accurate to say that if we actually want to identify just the effect of smoking on cancer, that you need to be able to account for those things. And then they did, right? They would control for whatever they could control for. They did some other stuff to account for the stuff they couldn't control for. But they needed to be able to know what those things were in order to be able to pin down just the thing that they're interested in. So understanding the setting of where your data comes from, which means understanding your data generating process, is crucial to being able to know what are the other things that could be going on that you need to block out in order to identify your effect.
Interesting. Talking about causal diagrams, in your book, you have covered, about directed acyclic graphs, that is DAGs. Historically, economists haven't viewed it very favorably, I can say. There was the famous debate between Guido Imbens and Judea Pearl on the merit of DAG. What is your view on DAG? Do you think it also runs the risk of someone falsely claiming causality just merely by drawing it?
Yeah. So what a DAG is, what a directed acyclic graph or a causal graph is, we mentioned that data generating process,
Hmm.
right? It's the set of laws that explain where things come from, right? Why your data might be the way that it is.
Hmm.
And what a DAG is, what a DAG is it's a way of visually representing that dot that represents smoking cigarettes. Here's a dot that represents cancer. We're going to draw an arrow from one to the other saying that cigarettes might cause cancer. But also, here's, your level of risk taking. People who like to take risks. That's going to cause you to smoke cigarettes. That's also going to cause you to get cancer for other reasons, right? Maybe you start drinking stuff that causes you cancer, right? And so that's the DAG, right? It's just taking those relationships and representing them graphically.
Hmm.
And so I think that these are very useful, at least pedagogically. They make it a lot easier to learn about causal inference because you can see very clearly what the research design problem is in front of you, right? I mentioned you have to come up with that list of alternate explanations of why two things might be related to each other, right? Why we see the data that we see.
Hmm.
And the DAG, once you've drawn it out, makes it very obvious what those things are, right? So it makes setting up your research design, knowing what it is you need to account for, knowing those alternate explanations, very easy to do. Now, in actual applied research, right? So I mentioned we talked about there being two different sort of big streams of thought, and the economics one doesn't really use DAGs, or at least has traditionally not used DAGs to represent things. And there's the debate sort of goes actually to a second level of what the theory is, which is what's called the set of structural equations. So I
Hmm.
mentioned, you got all these dots and you got these arrows pointing between them for the directed acyclic graphs for the DAGs. And what that really represents is not just, one thing causes another, but there's some equation that describes how one thing causes another, right? It's not like smoke one cigarette and suddenly you have cancer now immediately, right? It's that as the number of cigarettes increases, as you smoked over your life for the length of time, for the amount of cigarettes, it increases your probability by some amount in some function in some formula, right? That function or formula or whatever, and the ways in which smoking interacts with all the other stuff that you do, that's called the structural equation. That's a lot more complex than just drawing the DAG. There's a whole equation underneath that actually describes what the data generating process is in a lot more detail, right?
Hmm.
And if you are doing formal causal analysis, you want to think not just about the DAG, but also about that set of structural equations that actually describes things, right?
Hmm.
And so economists also have their own version of structural equations, right? Where we don't have not really been using the DAGs, but we have been using structural equations where we write down how we think one thing causes another.
Hmm.
And so in both systems, you have that same idea that you want to write down these equations, and these equations will tell you how to identify your effective interest, get rid of the things that you don't. Now, in terms of where the DAG, that economists will point out that there are certain things that you would not see on a DAG, right? So, let's say, for example, that you're doing some sort of research design where the important thing is that let's say that you're interested in the effect of insurance coverage on how fast you drive, right? Maybe if you have a lot of health insurance, you're willing to drive faster, right? Let's say that. And let's say that your level of health insurance is going to affect, uh, let's say, your chances of surviving. No, let's say your level of health insurance always affects that. It always affects it. It is in fact true. If you go from no health insurance to some, that is going to change how recklessly you drive. You're like, oh, I got some insurance that's going to make me drive a little bit more recklessly, right? And I'm not saying this is true. I'm just saying this is an example of something you could be studying, right?
Hmm.
But then it sort of it flattens out, right? It still matters after that. The more health insurance you have, it still matters, but like a lot less, right? It's a very flat curve. So that change in shape, right? The fact that it's a very steep effect first, and then a very shallow effect, that would be in the structural equations, that shape, that function, that relationship, but it would not show up in the DAG, right? And so you would not be able to use a DAG by itself to study anything in that scenario, where the thing that's important is the functional form, the actual kind of function relating those two things, right? And so
Mhm.
if you're just using the DAG and not using any structural equations at all, you will miss out on certain kinds of research designs that are in fact quite plausible and useful. That's one thing. Um, there are also certain problems that are very difficult to solve with a DAG alone that also, again, you need the structural equations to solve. Now, once you have the weaknesses of the DAGs, the system that uses the DAG, Judea-Pearl system, the structural equations can solve pretty much all those problems. Because again, the two sort of schools of thought that we have here, right? The economics one where they use what's called potential outcomes from Donald Rubin, and the Judea-Pearl one where they use what's called structural causal modeling. They can solve all the exact same problems. They are mathematically identical once you get past sort of the surface level of them.
Mhm.
But again, there are problems that make them harder and easier to solve, and or that become harder or easier to solve in those systems. And there are
Mhm.
certain kinds of problems. For example, anything that has to do with an equilibrium, like supply and demand equilibrium, that economists care a lot about, that
Mhm.
are not particularly easy to solve in the structural
Yeah.
causal modeling Judea-Pearl system. And you have to they can be done. You bring in the structural model, structural equations, and suddenly you can do them again. Or those functional form problems, again, you bring in the structural equations and you can do them suddenly, but the DAG itself doesn't do it.
Mhm.
And so it is accurate to say that if you are trying to just use the DAG, that there's a lot of problems you can't solve, or that. But you can just say, well, bring in the structural equations. But at that point, it doesn't matter which system you use. You can use
Mhm.
potential outcomes. You can use structural causal modeling, and you can get the same answer either way. And so it is also true in those cases. The DAG does not really add anything. You didn't need it, right?
Mhm.
So the other question that you had was, does the DAG make it easier? Possibly, does just say, well, I've solved the problem because I've drawn a DAG.
Yeah.
And that's definitely true. I think that, we right now we have what we called in potential outcomes in economics, we would call it an ignorability condition, which means
Mhm.
that I have written down all my equations of how I think these things relate to each other, and I'm just going to assume that these two things are unrelated to each other because that's
Mhm.
very convenient for my identification. It makes it easy for me
Mhm.
to statistically identify what I'm interested in if I can just say, I got it, right? These things are unrelated to each other. It's basically like the random. Um, and that lets us get away with a lot of stuff, right? If you can just say these two things are unrelated to each other, then suddenly you've solved a problem for yourself. You have to actually prove that that's true. And in more careful work, they will, right? You can do the exact same thing in a DAG, right? You can, if you once you've written down your DAG, you can just write down a DAG that's simpler than the truth. And you can get away with a lot by doing that, by saying, this DAG just says I need to control for these three things and I'm good. When actually you need to control for a bunch more, you just should have put those things in your DAG and you didn't, right? I think that both of these ways of getting away with something are pretty equivalent. I think that the fact that we see it less, well, we see it differently in DAGs is just because they're not as common yet. And that if they were equally common, they would be equally as likely to try to get away with things in both systems. I
Mhm.
don't think particularly that either system is better than the other at avoiding bad research. You can do bad research in any way, right?
Mhm.
You can try to get away with stuff in both systems, and I don't think that one necessarily makes it easier to get away with than the other.
Mhm. You talked about the example of whether smoking causes cancer and how it was proved not via traditional RCTs, but quasi causal experiments. Do you think when quasi causal experiments are done right, they are kind of equivalent to RCTs?
Yeah. So again, a quasi experiment is a case where you're looking out in the world for the world to have done an experiment for you, right? So one example of this is like, what's the effect of being in the military on your later income?
Hmm.
Right? It's an interesting question. Well, you can look back to say a randomized draft. Let's say that it's wartime and you are being drafted into the military. You can't choose to go, right? 'Cause being able to choose your own treatment it gives you a lot of problems in causality.
Hmm.
But it's randomized. It's random whether you get called up for the draft or not, right? That's a case where the world has sort of done a randomized experiment for you, and you can look at people who were drafted, either were or were not, just by random chance, and among those people, you basically have a random experiment, right?
Hmm.
And so, I do think that. So the question is a randomized is a quasi experiment as good as an RCT, right? Done right. And I think it's not about doing it right. I think it's about
Hmm.
finding a really good quasi experiment, right? I
Hmm.
think that the most fortuitous quasi experiments that exist in the world are as good as RCTs, possibly better,
Hmm.
because doing an RCT is not in the real world. right? You are
Hmm.
introducing some artificiality into the system. You know,
Hmm.
you have to recruit people. Sometimes people don't want to be recruited. Why did they choose to do that? Right? And that sort of puts a bit of a wedge in the idea that everything is completely random. Also, people know they're being studied, right?
Hmm.
Things are being administered in a laboratory setting in many lab experiments. A lot of these things are artificial, right?
Hmm.
And so, if you can get that level of randomization, which RCTs do give us, and it's very nice, if you can get that without having to fake it, that's probably better, right? Where, you know, if you actually have a true source of randomization out in the world, you're likely to get a more accurate result than an RCT, not a less. However, in the real world, we don't usually get quite that clean level of RCTs, right? Or quite that clean level of randomization, right? People can dodge the draft in the example that I gave, right? They have ways of getting out of the treatment they've been assigned to. Different kinds of people are more or less likely to dodge it. Some people are sick, so they don't have to go into the military, right? All these different things sort of introduce kinks into the whole randomization thing. And so I would say a typical quasi experiment is not going to be as clean of an identification, as good of a randomization as an RCT. A really good quasi experiment where you found in the world a really good source of randomization, at that point, there's a bit of a trade-off with RCTs. It's probably not truly quite as random as a really good, well-done RCT, but it is more realistic. And so at that point, I would say yes, it is on par with an RCT when you have a really truly random source of real world variation. And then in terms of how well the research itself is actually done, you know, that's important too. But the thing that can make a quasi experiment, you know, competitive with an RCT is the real world happening to have provided you with a really good source of randomization.
Yep, I think that was a great explanation. When we are trying to, establish causality, of course, there is temporality, but the other biggest thing that is needed is, counterfactualness. How important are counterfactuals in establishing causality?
Yeah, so a counterfactual is the world that didn't happen, right? I
Hmm.
mentioned the problem where I want to know what the effect of the pill was on your health. So I give you the pill and I don't give somebody else the pill and I compare you two. But what I really wanted to do was to compare you against the counterfactual world where you did not take the pill, right? That's what I want. And so I think thinking about counterfactuals is crucially important to causal inference, right? It's what's called the fundamental problem of causal inference. Again, if you're in the Donald Rubin school, people coming from the Judea-Pearl school are less focused on counterfactuals. But the thing that they are focused on instead is something that's very much like a counterfactual, right? Called the do operator, which is not technically counterfactual, but is for colloquial purposes close enough to consider to be pretty
Hmm.
much the same thing. So you have to think about counterfactuals, right? You have to think about what is happening in the world in which something different is, right? Because that's what we're interested in causality, right? We want to know what is the effect of this thing. What we're really asking is, what would the world look like if this other thing had happened, right? If I hadn't smoked, would I still have gotten cancer, right?
Hmm.
That's the question. And so
Hmm.
yeah, very, very, very central.
Hmm. In your book and in your YouTube tutorials, you emphasize on knowing statistical concepts like p-value, confidence intervals, power a lot. Uh, what is the significance of knowing all these statistical concepts? Are they really important?
Yeah, so we do use statistics a lot, right? In the process of performing causal inference, right? Once we have our research design,
Hmm.
we know what we need to adjust for or account for or get rid of. But then how do we actually do that,
Hmm.
right? To actually do that, you need statistics of some sort, right? You need actual data, because that's the whole idea. You're looking at the data and you're trying to explain it. And so I think you do need a very strong grasp of statistical concepts to do causal inference purely because we need to apply the research design that we did and account for the fact that we both have all these alternate explanations we need to account for, and we just have noise in our data that we need to account for. And so
Hmm.
you have to properly deal with both, or else you're not going to be able to properly get at the causal effect that you're interested in.
Hmm.
And so understanding things like, you know, confidence intervals, p-values, noise in the data, how can you separate out different things? How can you control for a variable? Those are key to being able to actually implement causal inference designs.
When we learn any programming language, the hello world example is a classic. And when we learn any statistical algorithm, linear regression is the first hello world kind of equivalent that is being taught. How important is linear regression to establish causality? Is it one of the, main tools out there?
Yeah, so what linear regression is that we're using an outcome variable and we're trying to predict that outcome variable with a bunch of other predictors, right?
Hmm.
We have a bunch of things like say, okay, I want to know what your health is. I have how many cigarettes you smoked. I have how much you exercise. I have your parents' health. All these things that might predict your health level, right? And linear regression says, okay, I'm going to see how each of these individual components predicts together, accounting for the ways that they interact with each other, at least in a linear way, right? Which we mean by, we're just adding things up to each other and, sort of drawing a line. And so I would say, linear regression, uh, I think in economics, that is the first tool, right? That is sort of the main tool. That's not even true necessarily in a lot of other fields where they might be a lot more likely to use something like an ANOVA, which I guess technically is linear regression under the hood. Or, in machine learning, they use linear regression less. They use some other tools. So uh, linear regression is very important because it's a very intuitive and sort of first step way of being able to account for those alternate explanations. I mentioned how all the different predictors, it accounts for the ways that they interact with each other. And so if there is the case that people who are more likely to eat healthy are less likely to smoke, for example, and that might affect their outcomes, it will account for that fact. It will say, oh, yes, okay, I recognize there's a relationship between eating healthy and smoking. And so I will, if I'm looking at the effect of smoking, I can take out that part of the relationship, right?
Hmm.
And linear regression does that, which makes it a very useful tool for causal inference.
Hmm.
Um, I think you could totally get away with doing causal inference without ever touching a linear regression. There are certainly other ways to do that same process. The process is what's important. Linear regression is not the important part. And you can also use linear regression for non-causal purposes very easily and sometimes accidentally, right? Um, but it is a very intuitive tool. I think that, there's a lot of reasons not to use it, but I think there's also a lot of reasons to use it. That it solves this causal inference problem so well that even some of the statistical weaknesses of the method are sometimes worth overlooking to be able to get to just something that works so well at addressing this causal inference problem.
Hmm. In my field of market mix modeling, we use multilinear regression a lot. How do you think linear regression or multilinear regression are implicitly causal in some ways? What are the common misconceptions around regression when associated with causality?
So I think that linear regression is and other forms of regression are not necessarily causal, right? You can
Hmm.
easily use them in a non-causal way. They do sort of imply a causality in the sense
Hmm.
that as you are reading a regression table, it is very tempting to say, I see a point 4, therefore this thing increases causally the other thing by point 4,
Yeah.
right? Very tempting, but often not true. In fact, I'd say probably most of the time not true, unless you've done a very careful job of identifying the causal effect of thinking what are the thing what is the version of the regression that I need to run to get
Hmm.
the causal effect.
Hmm.
And so linear regression is sort of sneaky in that way, in that it has an outcome and some predictors, and it is very tempting to say that the predictors cause the outcome, but they don't. They just predict the outcome, right? Linear regression, in fact, by itself is never causal. It's our interpretation of it and saying, well, I think that I've included the things to say that the correlation that I've gotten out of this linear regression is a causal one, right? There's a common phrase you might hear, correlation is not causation, right? And that's true. Correlation and causation are not the same thing, right? Correlation is just in the data. I observe these two things go together. Causation is one of those things cause the other. But the sort of next step of that is that, well, what is causation then? It's just certain correlations. Certain correlations have a causal content to them. The question is, which correlations, right? If I look at the correlation between randomly giving you a drug in an RCT and you getting healthier, that correlation is causal. Or if I've carefully mapped out the data generating process, got all the other explanations it could be, and gotten rid of all the other ones, well, then that correlation is also causal, right? So really, linear regression only gives us correlations. It always gives us correlations. And then we can use our research design knowledge to say whether or not that correlation has a causal interpretation or not. So most of the time, it's not causal. But if you do a careful job, it can be.
If we control for all the variables, can we say that this particular correlation is causation in the linear regression perspective?
So the question is, if you control for all the variables, can you call it causal? That depends what you mean by all the variables, right? So just taking all the variables that are in your data and tossing them into your regression, that's very unlikely to give you a causal effect,
Hmm.
right? And in fact, it could hurt your causal effect. There are certain variables where you could start with a causal effect and then you add a control and it ruins the causal effect, right? And so controlling for all of the variables that the research design process says you should control for, that will give you a causal effect.
Hmm.
Uh, accounting for some maybe nonlinearity or something like that. But, in general, you control for the stuff you're supposed to control for, yes, you can get a causal effect every time. If you actually know all the variables you need to control for and you have data on them, you can get a causal effect that way. But often that does not map onto just tossing in all the variables that you have, because A, some of those variables maybe you shouldn't be controlling for, and B, you're probably leaving out variables that you just don't have data on, but you need to control for anyway.
Hmm.
And so usually, yeah, just tossing in all the variables will not do it by itself.
Hmm. Understood. Talking about other types of effects, there is the ATE, ATT, CAT, LAT. Can you please unpack these four terms for our audience?
Mhm. So these are what are called treatment effect averages.
Yeah.
So I've been talking about the effect of things, right? That's the title of the book, right?
Hmm.
But really, there is no such thing as the effect. There's not a single effect, right? Do cigarettes cause cancer? Well, yeah, I don't know, but also, does what is the effect of smoking on cancer in you, right?
Hmm.
Maybe for you, you have some magical gene that will make you never ever get cancer. It doesn't matter how much you smoke, you'll never get it. The effect of smoking for you is zero, right? But the effect over here for this person over here, maybe they're really sensitive to tobacco and the effect is very strong for them, right?
Hmm.
So different people have different effects, right?
Hmm.
Different individuals. It always varies from one person to the next. We would never expect that really the effect of one thing on another is the exact same for every single person. Okay.
Hmm.
So we really have individual effects. For each individual person, they have their own effect of whatever the thing is.
Hmm.
And unfortunately, in causal research, we are rarely able to identify every individual person's separate effect. It's usually just not feasible
Hmm.
because to do that, you would really need to be able to say, okay, I want to compare you to yourself in the counterfactual universe, which is rarely possible, right?
Hmm.
But what we can do is we can take averages. I can say, well, I know that some people are going to be more affected and some people are going to be less affected. I can't get that whole distribution, but I can average them out. And so, depending on the kind of analysis that you do, you might be able to get what's called an average treatment effect, which says, I don't know how much the effect of smoking is for you personally, but I do know that for people in general, it's this, right? And that's one way of averaging out all the treatment effects. Now, depending on the kind of research design that you do, you might not get that. Sounds like often that's what the thing that you'd want, but you can't always get that. So, for example, let's say that we're doing one of those quasi experiments, right? Let's say that I happen to find that, oh yeah, in this part of the world, cigarettes randomly got more expensive at one point, and people had to stop smoking because they couldn't afford it anymore, right? That's a sort of random experiment that I can look at. Um, but that's only going to tell me about the effect of smoking in that area, right? And so that's what's called a local average treatment effect, where I
Hmm.
can get the average effect, but only among a certain part of the population. If that area happens to be different, maybe this is some remote fishing village where everybody has the I can't get cancer gene or something, right? Then I'm going to say, oh, look, smoking doesn't have an effect on cancer, but really it's just it doesn't have an effect in that group, right? It might well have an effect in the broader population.
Hmm.
So that's one way in which we might get a different kind of treatment effect average. There's lots of other ways. You can get conditional average treatment effects. Maybe the effect is different for men and for women, right? You can get the average treatment on the treated, which is I can get the effect just among people who actually did happen to get the treatment, right? What's the effect of education on your outcome? Maybe I do some analysis that can't tell me what that is for everybody, but it can tell me what it is for people who chose to go to college or
Hmm.
something like that, right? And so what these do, it's not like you can just pick whichever one's the best. Often it has to do with the research design that you have will only allow you to get one of those things. But they answer different questions, right? About what it is that you can actually do with this effect. Right? If you have an average treatment effect that applies to everybody, that might tell you what's going to happen if I ban cigarettes for everybody,
Hmm.
right? If I have a conditional one that tells me the difference between men and women, or between older and younger, or between whatever it is, that might tell me how the effect might be different in different areas. Maybe it tells me, oh yeah, hey, if you can only ban cigarettes in one area, do it in this one because they're the ones who are really going to get cancer, right? Um, and so it lets you do different things with the kind of effect that you estimate.
Moving on to the second section of your book, the toolbox, you talk about matching. How important is the concept of matching? Is it somewhat related to the concept of counterfactual that we just talked about?
Yeah. So there's two big approaches in causal inference to accounting for those alternate explanations, right? Getting rid of everything except for the one that you're interested in. One is regression. And what regression does is it says, I have some data on this explanation over here, right? And I'm going to see sort of how related that is to our treatment and how related it is to our outcome. I'm going to subtract out that effect. And once I've subtracted it out, it can't possibly affect anything anymore, right? And that's the way in which I'm going to knock down all these explanations is by simply statistically subtracting out the effect of those things, right?
Mhm.
Matching takes a different approach. It says, okay, I've got all these explanations. And what I'm going to do is I'm going to find people who are basically the same on all of these things, except for the treatment I'm interested in. They're all the same, right? They're the same level of health, same level of risk taking, the same level of all these things.
Mhm.
And once I do that, if I compare people who are the same on everything except for my treatment, well, then these things can't possibly be affecting anything because everybody's the same on them, right? It doesn't matter if being more of a risk taker might make you more likely to get cancer or whatever, right? Because everyone's the same level of risk taker, right? So that's the alternate approach that matching is taking. Instead of statistically adjusting for differences between people, it simply looks
Mhm.
for people who have no differences in the first place, right?
Mhm.
And so I think this is a very important concept. It uh, is more plausible, I think, to a non-statistical audience, right? If you tell people, oh, I accounted for these things, oh, how did you do it? Well, I statistically adjusted. That's a lot harder to understand than saying, oh, I found people for whom they were basically the same, right? Except for
Mhm.
this one big difference, right? Um, so that's one thing. It's a lot more plausible. It
Mhm.
solves the problem in a slightly different way. So it allows you to get at, we talked about treatment effect averages. It's a slightly different treatment effect average. And it can also be combined with, regression, right? There's no reason to just have one or the other, right? I'd say the big downside of matching is that it is, if you have a lot of things you need to control for,
Mhm.
it can get very difficult, right? It's hard to find people who are the same as you on nine different qualities, but different on the 10th,
Mhm.
right? There just might not be that many people, right? Like that. And so if you've got 1,000 people who are treated, it's hard to find 1,000 people who match them who are untreated. And so you have to sort of make your comparison a bit more lax in order to allow that to happen. And then how lax do you let it get, right? And so there's a downside there as well. I would say it's a crucial tool, right?
Mhm.
There are settings in which it's going to perform better than regression. There are settings in which it's going to perform worse, and it's good to have sort of access to all those tools. There's no reason to get rid of one, just because it's not the standard in whatever field you happen to be in.
So your book and the section toolbox in particular talks about a lot of tools like DID, difference in differences, regression discontinuity. So let's play a small game, which I call
Mhm.
the rate the causal assumptions game. As you know, in
Okay.
statistics and causality, there are a lot of assumptions. So you can give a brief, introduction of the topic, and then tell me whether the assumptions behind them are impossible, possible, or not. So I'll
Great.
just bring up my screen. Let me know if you can see my screen. Is my screen visible?
Oh, there it is.
Yeah. So first up, we have the DID's parallel trends assumption. So if you want to unpack for the audience what is DID and then what is parallel trends, and then you can go ahead and tell me if the assumption is reasonable, unreasonable, or impossible.
Yeah. So DID difference in differences. This is a research design where the idea is that. So let's say your first guess. If you were going to start out building the idea of causal inference, right, just from scratch, you'd never heard of any of this. Probably the first thing that you do is you say, okay, I want to know if this pill makes you healthier. So I didn't have the pill, then I took the pill, and then I got healthier,
Mhm.
right? That's your sort of first step causal inference, right? And the problem with that, obviously, is that you might have gotten better anyway, right? That's the sort of problem with that first thought. And so, what difference in differences does is it says, okay, all right, we have you. You were sick. You took the pill. You got better. Let's compare you to somebody who was sick, didn't take the pill,
Mhm.
right? Did they also get better? If they did, then you probably would have gotten better anyway,
Mhm.
right? And so that's the basic idea of it, right? And you can apply this more generally. I want to know whether the increase in the minimum wage reduced employment. Well, I can say, well, I had this level of employment, then the minimum wage went up, and then employment went up or went down, right? Let's say. Well, maybe that would have happened anyway. Maybe the economy just got bad. So I'll compare my city against a city that didn't raise the minimum wage and see if their employment also went down, right? And I will
Mhm.
compare those two things. Now, this works as long as the parallel trends assumption holds. And what parallel trends says is that if the treatment hadn't have happened, those two
Mhm.
groups that we're comparing, they would have continued in the same direction, right?
Mhm.
So I'm assuming basically when I say, okay, that city that didn't raise their minimum wage, oh, their employment went down too. I'm
Mhm.
assuming that if I had not raised my own minimum wage, that mine would have gone down the exact same amount that theirs would have. Okay, that's the assumption that needs to happen, right? Similar with the pill. If I observe that they didn't take the pill and they got better too, I need to assume that if I hadn't taken the pill, I also would have gotten better just like them because I'm making that comparison. I'm sort of assuming that whatever
Mhm.
happens to them is the counterfactual for me. Now, is this
Mhm.
plausible? In a technical sense, no. It is not plausible, really, that this is ever going to be perfectly true. Now, it might be close to true, though, and that we can work with that. You can work with if you think parallel trends, maybe isn't perfectly true, but you have no reason to believe that it's really, really wrong. There are ways that you can account for that sort of kind of wrongness. There's something, for example, called honest difference in differences, which allows for some violations of that assumption. So I would say, in a strict sense, no, implausible, unlikely to really ever hold, but
Mhm.
could get close enough to work,
Mhm.
and that's what makes it so valuable. Um,
Okay. Mhm. Yeah, so where
Next
would
up,
you put DID's parallel trends assumptions
oh,
in
I'd
between?
say reasonable,
Okay.
uh, maybe somewhere between reasonable and unreasonable, because it's
Okay.
literally, in a sense, never true, but you can work with it.
Got it.
Um,
Yeah. Next up is sharp cutoff rule in regression discontinuity designs.
So regression discontinuity design, these are designs that apply in cases where some sort of treatment is applied at a cutoff, right?
Mhm.
Let's say I want to know, what's the effect of this blood pressure pill on your
Mhm.
blood pressure? Does it work, right? And let's say that we give you that pill if your blood pressure is 180 or above. Let's say, just to pick that's not even a blood pressure number. Let's just pick, yeah, 180, whatever. 180 over 60. I don't even know if that's a good blood pressure or not. If you're above that, you get the pill. If you're below that, you don't. Okay. And so what you can do is you can say, okay, well, if you have a blood pressure of 179, you're almost there, right? Somebody who has a 179, somebody who has a 181, those are basically the same. Those are comparable, but one of them got the pill and one of them didn't, right? And so by comparing those two people who are very similar, but one of them's just over the line, then you can compare them and you can say, okay, well, the differences between them must be because of the treatment itself, right?
Mhm.
And there's lots of things like this. If you want to get food stamps, you have to earn under a certain number of dollars, right? And so if you're just above that, you don't get it. If you're just below that, you do, right? So there's lots of cutoffs like that in life, in different areas. And so there's lots of assumptions that need to be true for this to work. One of
Mhm.
them, if you're doing what's called a sharp regression discontinuity, which is saying that just below the cutoff, you don't get the treatment at all. Just
Mhm.
above it, you do. I would say that this one varies a lot from context to context, right? In some
Mhm.
contexts, it's very implausible.
Mhm.
Really, anywhere where somebody has a little bit of say over their own treatment, right? If you can say, okay, I know I have a 179, but I'm just going to harass my doctor until they give me the pill,
Mhm.
right? That's a real world thing that might happen. And so in that case, you would expect a little bit of porousness there, right? Then the 179 person who didn't get the pill is also a 179 person who's not aggressive enough with their doctor to get the pill. And you're
Mhm.
introducing other factors into it. Um, and so I'd say this is very context dependent. There are contexts in which it is really true that the sharp regression discontinuity applies.
Mhm.
And there are other contexts in which it gets a bit fuzzier. There's actually literally a version of regression discontinuity called fuzzy regression discontinuity, which
Mhm.
allows for this. Um, and so I would say, but once if you think that it is likely to hold in your area, then I'd say it's a very solid design, right?
Mhm.
So I'd put it somewhere in reasonable, context
Okay.
dependent reason.
Okay. Understood. Next up is synthetic control methods, synthetic twin assumption. What
Yeah.
do you think about it?
So what synthetic control is that you've got so we're back in that first thought. The first thought of causal inference is I didn't take the pill and then I took it and then I got better, right? And so what synthetic control does is it says, okay, we've got some group or some region or some person or whatever,
Mhm.
they were going along. Here's like maybe their health level before, and then they take the pill or they get the policy or whatever it is, and then things change afterwards, right? But again, maybe things would have changed anyway. And so like difference and differences, what synthetic control does is says, okay, I'm going to compare this to get the policy at the same time. And I'm going to compare their trend lines as well. And the synthetic part is I'm going to take all those comparison people and I'm going to combine them in a smart way such that before the policy happens, before the treatment happens, the person who got the treatment, right, whatever weird shape their time series takes, is going to be matched exactly by the other people, right? I'm going to pick a mix of the other people that matches them really, really well. That's the synthetic control. And so I think that this is a very plausible one because you can check it really easily. It's really easy to check visually whether or not you've done a good job. Generally, if you are capable of finding a mix of comparison groups that really closely matches the time series that you had, like if your time series is all weird and looks like this, and it just so happens that the groups that you're comparing to also look exactly like that, it seems very plausible to me that in the post-treatment era, they would have continued to look the same if not for the treatment. And so any deviation we see must be because of the treatment. So that one I think counts as pretty plausible to me, or at least in the cases where it's not plausible, you can tell, which is the real key here, right? All these assumptions can fail, right? They can be false in certain scenarios. The question is, A, can you check it? And B, are those scenarios just all the scenarios, right? In this case, I think there are lots of scenarios in which you can apply it, and if it doesn't work, then you can see it. So I think it works pretty well.
Understood. So where would you place it? Somewhere reasonable?
I place it in reasonable.
Okay, great. What about the stable treatment value, SUTVA?
So SUTVA. So this basically says that we know what the treatment is, which is a weird assumption to make, right? But it's sort of like when you start getting into like advanced math and like, oh yeah, we assumed that 2 + 2 = 4, and you're like, okay, well yeah, but oh yeah, we spent 100 pages to prove it. Well, it's sort of like that. So there's two things that go into this. One is that when we say we know the effect of one thing on another, right? That there's an idea of what that thing is, right? If I say I want to know what the effect of raising the minimum wage is on employment, well, raising the minimum wage might mean one thing in one area and mean a different thing in a different area, right? Let's say I live in an area where the minimum wage is really well enforced, right? If you try to pay somebody less than the minimum wage, they're going to catch you, they're going to sue you, you're really not going to want to do that. In another area, maybe the enforcement's really lax, right? They also raise the minimum wage, but also nobody really pays attention to whether you're being paid the minimum wage, and it doesn't actually happen, or, you live in an area, a tourist area where everybody is working tipped and the minimum wage doesn't actually apply to anybody, right? In that case, I can say the same thing. Oh yeah, here's a case where the minimum wage went up, so the treatment is the minimum wage going up, but it means such different things in different areas that they're really not comparable, right? So that's one thing. The other has to do with spillovers, right? Let's say I want to know the effect of raising the minimum wage, and I live here in Seattle, and we did raise the minimum wage not too long ago, right? And so I want to know the effect. So I'll say, okay, I need a comparison, right? I see what happened to the employment here in Seattle, but maybe that would have happened anyway. So I need to compare it to a different city that didn't raise their minimum wage. So I'll pick Bellevue. Bellevue's a city that's right next to Seattle, right? They share a border. You can drive there in 20 minutes, right? But they didn't raise their minimum wage. Compare them, right? Except the labor markets of Bellevue and Seattle are very closely tied together. A lot of people who live in Bellevue work in Seattle and vice versa, right? And so when we raise the minimum wage in Seattle, that will also affect the level of employment in Bellevue, right? And so if I'm comparing the two of them, I'm going to get some bleed of the effect into Bellevue. And so my comparison is not a very clean comparison, right? So that's the other part of SUTVA. So there's two things going on. One, I need to have an idea of defining what the treatment is. And two, when I say that the treatment was applied, I need to know who it was applied to and who it was not applied to. So I would say this is one that is often overlooked. And especially that first one, I think people who are doing causal inference tend to ignore it a lot. And so we don't do quite as good of a job of making sure that this is reasonable as we could. I would put this in the unreasonable category, and in certain circumstances, impossible. You could probably straddle the two.
Okay. And the last one is perfect balancing in propensity score matching. What do you think about perfect balancing?
So propensity score matching is a version of matching. We talked about, we have these factors except for one. So when you compare you to me, we're basically the same person. Um, Propensity score matching is a version of that where instead of finding somebody who is similar to you on all the characteristics, we use those characteristics with regression to predict your treatment, to predict whether or not you got the treatment. And then I find somebody who is as likely as you to be treated, right?
Mhm.
So I say, given all your characteristics, I think there was a 25% chance that you were going to get the treatment, and you did. I also had a 25% chance of getting the treatment, but I didn't. So we are comparable in that way, right?
Mhm.
What perfect balancing says is that well, there's a couple of different things that you can mean by it, but often what it means is, okay, you had a 25% chance of being treated. I also had a 25% chance of being treated. Let's go back to those factors and see if we're actually similar on these things, right? Because if the concern that we have is that we're different on all this stuff, then, if we are both 25%, but you're 25%, likely to smoke because you're a big risk taker, I'm a small risk taker. I don't like to take risks, but my parents smoked, and so that makes me more likely, right? We're both 25%, but for very different reasons. That can be an imperfect balance of the matching variables, right? Even though we have similar percentages, we're still not comparable. And so this is one where you just got to get lucky, right? You just got to sort of hope that when you match, you end up with good balance. So again, sort of like the synthetic twin one, maybe a little bit less so, because I think this is less likely to actually happen. This is one reason why you might want to match in a non-propensity score method way.
Mhm.
Um, but it's very easy to check. You can very easily see whether you got good balance or not.
Mhm.
So I'd say I put it somewhere between reasonable and unreasonable in that it's unlikely to strictly ever hold, but at least you can
Mhm.
check it.
Understood. Yeah, this ends this particular little game. Dr. Nick, thanks for this. Let's move to the other questions.
Sure.
Yeah, in your book, you also, have a particular section about event studies. Are event studies causal?
Yeah. So event study, that's that first thought causal
Mhm.
inference that I mentioned, right? Something wasn't happening. There was an event. Something changed. Well, the event must have been responsible for the change,
Mhm.
right? And if this works, it's really good, right? Because it's very easy and simple to do, right? You just compare before to after, and there you go. There's your causal effect. I think that, and whether or not they're causal, you got to go back to the research design,
Mhm.
right? The research design tells you I understand enough about my setting to know what I need to adjust for to get my effect. And sometimes it really is just you can go before and after, right? The reason why event studies would not work, would not be causal, is maybe something else was changing at the same time.
Mhm.
If you can make the case that nothing else was changing at the same time, then you're probably good to go. A really
Mhm.
good example of this is in finance, right?
Mhm.
There's a lot of cases of very plausible event studies in finance because things change so quickly. You can
Mhm.
pretty cleanly assume that nothing else was changing at the same time. So
Mhm.
let's say, for example, you know, an earnings report comes out. Okay,
Mhm.
Walmart just released their earnings report. They lost 25% of their revenue. Nobody saw it coming, and their stock tanks immediately,
Mhm.
right? It's pretty clear that was the fault of the earnings report,
Mhm.
right? Nothing else. I mean, maybe other things were changing at the time. The economy is getting better or worse, whatever it is. But going from 10:59 a.m. before the report comes out to 11:01 a.m. after the report comes out, and the stock tanks 25% right at that exact moment, that's because of the report, right?
Mhm.
And so if you can pin it down that way, either because you have such a fast moving effect like that, where you can see the effect at a very specific point in time, so that you know it's really just whatever's happening then,
Mhm.
or if you have a really strong case for why nothing else is changing, like let's say that we're looking at some sort of time series, something changing over time, and it just doesn't change, right? This thing
Mhm.
has not changed for years and years and years and years and years, and then suddenly it changes, right? It's probably something that happened at that exact moment,
Yeah.
right? And so it's very context dependent whether you can establish that there's really nothing else going on, right? You're sort of hoping to luck into a case where the easiest thing works, but if it
Mhm.
does, sometimes it does.
Mhm. You recently released the second edition of your book. I'm sorry, I'm congratulating you pretty late in the
Thank you.
segment.
It's all right.
Yeah, but I did read the first edition thoroughly, but I'm yet to catch up on the second edition, to be honest. But I did notice in your LinkedIn post that you had mentioned that there's a new chapter that's been added, which is called the partial identification. What is partial identification? Why did it warrant a chapter of its own?
Yeah. So what partial identification is you've got your list of culprits, right? And you're trying to get rid of all.
Mm-hmm.
And well, here's a problem. Okay. I've got 10 different reasons why these two things might be related to each other, and I've got data on 7 of them. Well, there's a problem, right? If I still see a relationship in the data, it could be the thing I'm interested in, but it also could be these other things,
Mm-hmm.
right? And if you're doing traditional causal analysis, you're just sort of done. You're like, well, I guess I couldn't do it. I failed. I got to go home, right? I can't do this. Well, partial identification does this, says, well, what you really want to do is you want to assume that these things don't matter. We can't do that, right? It doesn't work. It's wishful thinking. But you can ask yourself, well, okay, I know that those things do matter. I know that I haven't gotten quite all the way there, but how close can I get? Right. So, the simplest version of causal inference would just be to assume that everything is random, right? Does smoking cause cancer? Well, I'll just assume that everyone who smokes is randomly choosing to smoke, right? And that's not true, but it would get you an answer, right? And so, we're not going to make that assumption because that would be clearly wrong. But what assumption can we make, right? We can maybe assume, okay, well, after we account for income and risk taking and parental factors and location and all this stuff, maybe then I think it's random, right? That's a weaker assumption. I'm assuming less about the world. I don't need to assume that it's perfectly random. Maybe I'm assuming it's random after I've control for all these things. But maybe I still don't even believe that. Maybe I think there's some other things I can't control for. Well, then you can ask, well, I'm going to make a weaker assumption still. I'm not going to assume that all the things I've left out don't matter, but I will say maybe there's a certain level to which I will allow them to matter, right? Maybe they matter, but they don't matter more than this much. And if I assume they only matter this much at most, well, then I can maybe put a bound on the effect. I can't say, well, smoking one more cigarette per day will increase your chance of lung cancer by 0.12%, but I can say smoking one cigarette per day will increase your chances of lung cancer by more than 0.01%, right? I might be able to get a range of reasonable results without having to assume things that I don't think are true. Right? That's partial identification. You are making fewer assumptions and getting a less precise result, but at least the result that you have is based on things you're pretty sure are true. And this applies in a lot of different contexts. And so I mentioned the one, maybe there's some stuff we can't control for. There's still some explanations left. I need to sort of handle the fact that I can't measure and control for these things, right? What range of reasonable results might I get from my effect? Saying, well, these things matter, but I can't control for them, right? But also think, all the assumptions that we talked about on the slide previously, we can do partial identification versions of that, right? Maybe I don't think that parallel trends and differences holds exactly. I just don't think it's true, right? But, if there's a deviation, I might be able to use some way of trying to say, well, I think the deviation is no bigger than this much, right? And if I can do that, well, I can say, well, if the deviation is no bigger than that, then the bound on the effect can be no bigger than this. And I can still get some information about my result without having to go all the way and assume something I don't think is true. So for why this is the new chapter, I think that this is an important and underused topic. Sort of the downside of causal inference and application is that, it requires you to make a lot of assumptions that are probably not true, right? Things like parallel trends, or like assuming that we have the full set of control variables.
Mm-hmm.
And this leads you to one of two scenarios, either where you're sort of ignoring the fact that you're assuming things aren't true, or giving up and going home.
Mm-hmm.
And I think especially in a lot of cases, like for example in the business world, you can't spend 2 years trying to make sure that you really are justifying your assumptions, or being able to say, well, I guess I can't answer that question. You have to have an answer, right? And also, giving up on trying to get a causal effect just because you can't get a single number is, I think, silly. I think it means that we are studying certain areas that are hard to study less, that we could get some information on. And so I think partial identification solves these problems, right? It allows you to get an answer and also be responsible and honest about how much information and knowledge you're actually gaining. It's underutilized, and so that's why I made the chapter. I wanted to make it more accessible so that it might become more popular. So that's sort of why I chose to make that the new chapter.
Well, you are the master of, explaining concept topics very simple manner.
Thank you.
Yeah, so I think that definitely evokes a lot of intrigue in me to, go and read that chapter, definitely. You have been in this industry for a decade and a half, and you must have seen the causal methods evolve. According to you, which of the causal methods have evolved more? Or is there some research that has excited you in the recent years?
So I'd say there's two strains. One is sort of in the more traditional causal inference, which is there's been a lot of work on difference in differences, right? Which is the
Mm-hmm.
most commonly applied difference or causal inference tool by far, simply
Mm-hmm.
because it applies in so many scenarios. All you need
Yeah.
for it to work is you need a treatment that went into effect at a certain time for some people, but not others. That's it. If you have that, you can do difference in differences, right? There's been a lot of work recently on figuring out what to do in cases where just the cleanest version is not what you're doing, right? Either,
Mm-hmm.
there's multiple different treatments that went into effect at different times, or maybe your outcome is binary, or, there's multiple treatments, right? There's all these different sort of wrinkles that really, because it's such a simple idea, it feels like
Mm-hmm.
you should just be able to simply adjust the whole process and it works. It doesn't work. You got to do a bunch of stuff.
Yeah.
And so realizing that and coming up with a lot of those solutions has been something that's happened a lot in the past 15 years. And so I think difference in differences is harder to do than it used to be 15 years ago, but is more likely to give you an actual correct answer. That's one
Mm-hmm.
thing. The other side of it is machine learning. So machine learning obviously has been a lot more common in the past, 15 over the past 15 years. We do a lot more of it. And now the thing with machine learning is that it's very predictive in nature, right? So I talk about predictive. What I mean is I want to know whether one thing predicts another. I don't care why necessary, right? And why is the whole thing of causal inference. So machine learning and causal inference is not a natural fit with each other. However, there are certain parts of the causal inference process that are predictive in nature, right? I've got all my explanations. I want to statistically remove all of them. That is a prediction process. I want to see what parts of my treatment I can predict with these other things and what parts can I predict of the outcome and then subtract those out. I can use that prediction process with machine learning. And so there's been a number of good advancements in machine learning that either use the predictive tools of machine learning to improve the causal inference process that allow you to do it in very high dimensional spaces with thousands of predictors and things you need to control for, or on huge data sets, which have been nice. And there's also been some developments in machine learning having to do with, I mentioned the treatment effect averages. You have a different treatment effect than you do, but we can't really get everybody's individual effect. That's still true, but when you have a huge data set, where you can compare lots of people, find lots of people who are a lot like you, even if you're a very unique and special flower, right? There's in a huge data set, there's going to be somebody. There have been a lot of advancements in being able to use that process with machine learning to get more personalized treatment effects. So those have been, I think, the things that have advanced the most in the past 15 years.
Interesting. You also have a separate website where you illustrate causality topics through animations. Where did you teach yourself this nice little trick of, animating things? Yeah.
So yeah, a lot of the tools that are in the toolbox part of the book, I have animations that show what those tools are actually doing to the data, like what does it actually mean when you control for a variable. I actually made those animations in the process of trying to teach myself the animation tool. That's where those came from. So GG Animate is an R package that allows you to animate ggplot graphs, which is a
Mhm.
ggplot, it's a graphing package in R. And so I was like, hey, that looks cool. What can I animate? And so I decided to teach myself how to do that with those causal inference tools.
Mhm. Yeah, coming to the final question of this podcast, I know a lot of people are, watching this podcast and they are thinking, how do I get started with causal inference? To them, what would be your, recommendation of resources? Of course, your book, The Effect, is an excellent recommendation. I would highly recommend it to anybody. Apart from that, do you have other recommendations?
Yeah, I would say other books to get started with, sort of one on more of the conceptual side. There's the Book of Why by Judea Pearl and Mackenzie, and that's a good introduction. That's it's rigorous with its theory, but it's not very math based, right?
Mhm.
That's it's sort of an introduction to the Judea Pearl way of thinking about causality and sort of different sort of concepts of what causality is. Another book on the sort of methods and application side is Causal Inference: The Mixtape by Scott Cunningham. That's another very good one. Um, and then you get into the more technical stuff, right? Those are not really the introduction, right? Those are just the introduction kind of books. There's also Causal Inference for the Brave and True by Facure. Uh, yeah, there's lots of good options out there for introductory causal inference books. In terms of getting started on doing it, I would say, read some of the research design sections of those books, right? How to draw a causal diagram, how to think about, some structural equations, and then just try to do it. take a setting that you understand a lot about and sit down and try to map out a causal diagram. I think it's a very instructive process to try to do yourself. Um, and from there, once you have it, it will allow you to identify causal effects. You can just get started going. There's sites called like DAGity, for example, dagity.net,
Mhm, mhm.
DAGITTY,
Yeah.
that allow you to draw out a causal diagram. And once you have it, it will tell you exactly what your research design needs to be. What are the things you need to control for in order to identify one effect on another, or the effect of one thing on another. And so just trying it out, I think, is a good place to start.
Mhm,
Just starting out, you'll probably miss some stuff, and you'll make some assumptions that probably aren't true. But I think this is a very because it is so because doing causal inference right is so closely tied to understanding the setting that you're studying,
mhm,
and knowing the context and where things come from and the data generating process.
mhm,
It is very easy to get started by just applying your common knowledge or applying the knowledge that you have of a given system. And so doing it is a good way of learning it in a
mhm,
way that's maybe a little bit less true for other forms of statistics or mathematics.
mhm. Great. Dr. Nick, thanks for your time. This was a really insightful session, and I'm sure, the audience are going to love it. A lot of rich nuggets of wisdom out there. And of course, I'm going to highly recommend people to, read the book, The Effect, the second edition, and of course, also catch up, Dr. Nick's videos on YouTube. Thank you once again, Dr. Nick. This was a absolutely brilliant podcast from you.
Thanks so
Thank
much.
you.